And we are interested in the representation of G hat. So this is a very big category. The most studied G hat module are those of highest weight module, so-called category O. So we have a nice result on the category O of the highest weight representation of affine Kac-Moody algebra. So this is we have BGD reciprocity, and we have Kazan-Lustig character formula. So this is very well understood, and there are many studies. And there are also a category of weight modules. So which are much more wild. And today I want to talk about objects here. So I want to consider a module which are not necessarily highest weight modules. So the problem I'm interested in is the structure of a category of weight modules, G hat module, as an abelian category. And so if you have ever studied weight module, you know that the representation theory here is much more difficult than that of category O. So this is very ambitious problem to consider. So I make it somehow problem nicer. And the question is how to make it nicer. And the slogan, so what I want to say in my talk is that the abelian category of weight G hat modules is as nice as category O, or when it is considered as modules of the corresponding Vertex algebra. So this is what I want to say, and I'm going to explain what I mean by this in my talk. So I only consider representation at non-critical level. So this is a level of G hat where a check is the dual Coxet number. And then to consider vertex algebra, I consider the so-called universal affine vertex algebra, which is just an induced representation of G hat, induced from one-dimensional representation of this parabolic subalgebra, where here GT acts as 0 and the central element acts as multiplication by this given number. So this is just an induced representation, but this has a structure of vertex algebra and called universal affine vertex algebra associated with G at level K. And so because this is a vertex algebra, we can talk about the representation of this vertex algebra. But the representation of this vertex algebra is nothing but smooth G hat module at level K. So here smooth means that the X tensor Tn acted on some element on the module is 0 for sufficiently large n for each element of G if we fix a vector from the representation. So you can think this vertex algebra as a kind of enveloping algebra of G hat because representation theory is the same. And today I want to consider a weight representation. So by weight module, I consider a representation which admit weight space decomposition or H tilde is the extended Cartan subalgebra. And each weight space is finite dimensional. So somehow want to restrict myself to the case when it has only finite dimensional weight spaces. And so this is quite big category. And here we have those modules which is positively graded. So this is M. So M is positively graded. So this is almost highest weight representation. And this contains category O at level K. So I'm interested in this category. But it's better to understand this intermediate category first. And we know that the simple objects in category O are those highest weight, irreducible highest weight representation. So this is parameterized by weights of G So this is H is a Cartan of G. So this is irreducible highest weight representation of G hat with highest weight lambda plus k lambda 0 in the standard notation. And then similarly, we can describe, so in particular, the simple object in one-to-one correspondence with simple object in the category O of G, finite dimensional G, because I was fixing the level. And then similarly, if you consider more a bigger category, which is positively weighted weight modules. So this is parameterized, in fact, simple weight G module, where this one is unique simple quotient of, again, induced representation. Where k acts as this number k, and the t acts, only g acts non-trivially on E. So, so this is, so for as long as we consider this category, classification of simple module reduced to that of the finite dimension G module. And so let me recall what simple weight G modules look like when G equals to SL2. So we have finite dimensional irreducible representation of SL2, which looks like, as we all know, like this. So if I draw weight vectors, we have highest weight vectors, and which generates everything by applying F and stop somewhere, and you can return to the highest weight vector by applying E to the lowest weight vector several times. And then we also have irreducible highest weight Varma module, which looks like the same but continues forever on the right. And we also have lowest weight representation, which goes another direction. But they are not all. There's another one called cuspidal representation, which goes in both, forever in both directions. So this is something very new in the setting of weight representation. And if you look at weight representation of you already find there that it's quite different from the behavior in category O. For example, the category of weight modules of SL2 does not have enough projectives. So there are no projective cover of a simple object in this category, which makes it hard to study this category. So nevertheless, classification of simple module is known. So that clock is stopped. There's time. Okay, so first, Fernando showed that any simple weight G module is either cuspidal or cuspidal like that, or parabolically induced. Parabolically induced from a cuspidal representation of of Lie subalgebra of small r rank. So the classification problem reduced to the classification of cuspidal modules, and which is done by Matthew. So he obtained classification of all cuspidal simple modules with finite dimensional weight spaces. So we know we have a good understanding of a simple classification of simple module of finite dimensional G. So we know the classification of simple object here, at least. I forgot to say this is called, so this one is called relaxed Varma module. And the quotient of this core is called relaxed highest weight module. And so how about more wilder category of weight representation, which are not necessarily positively graded? And this is already done by Slava with Til. How do you pronounce? The result of Tony Tilk. So they classified all simple objects, simple weight modules, smooth simple weight modules. And the statement is that this is all of this form where L is a simple objects, simple graded, positively graded weight modules. And then you twist action of G hat. This is so-called spectral flow in physics, so which is just a twist by the extended affine while group element mu, which belongs to co-weight lattice. So affine, extended affine while group is of the form as the semi-direct product with while group of G with co-weight lattice. And if you pick elements from co-weight lattice, you can twist the action of affine Kac-Moody on L, you get a new simple module. And this exhausts all simple weight module in this category. So this is very good. So we know classification of simple object in this category thanks to this result of Tony Zhu. So now the question is, how about the structure as an abelian category? And of course, this is a very difficult problem because this was already difficult for the SL2 case. So I want to make it somehow smaller, this category, but in some natural way. And for this, I use the vertex algebra technique. So this universal affine vertex algebra is not simple in general, because this is just an induced representation. So you can take unique simple quotient of VKG, which inherits a vertex algebra structure from here. So this is, again, vertex algebra. And this is a quotient of VKG by some maximal proper submodule N. And because this is a vertex algebra, we can talk about the representation of this vertex algebra. So the category of module over this vertex algebra form a subcategory of smooth G hat module. So it's a module on which all elements from so if you take any element, so I didn't explain the definition of vertex algebra, but if it's a vertex algebra have infinitely many multiplication. So for each element of this, there are infinitely many multiplication, which denoted by n, where n is some integer, and any element from this maximal submodule has to act as 0 for all n. So this is a condition to be a module over this simple vertex algebra. And this is form a full subcategory of VKG module, and which can become smaller if n is non-trivial. So you can talk about weight module in this category, and also a positively graded weight module, and or a module which belongs to the category O. So maybe I want to talk about the module which have finite lengths, which I don't denote by small n. This is finite lengths modules. And so you have all these full subcategories. And the most well-known example of such category is a case when K is non-negative integer. So in this case, this representation is integral. So in this case, we know that all of these categories are the same. So this category is the same as category in module in the category O. So any module is automatically becomes highest weight, because this constraint is so strong, and only highest weight representation can become a module over this vertex algebra. And in fact, this is the same as integrable highest weight representation of G hat of level K, which is in fact a semi-simple category. So a priori, this category is very wide, but in this case, this became so nice, and it just became a semi-simple category. But this is too nice, and it's not so interesting. So I want to relax the condition. So I want to consider more wilder, more general representation. But so there's a family of representation called Kac-Moody admissible representation. Which still lies in category O, but much bigger than the category of integral representation, but still quite nice as integral representation. So maybe some of you never heard of such representation. So let me define what is Kac-Moody admissible representation. So I await lambda hat of which is lambda plus k lambda 0 is called admissible if the following condition holds. So first condition is that this is regular dominant, which means a pairing with any positive real co-roots does not belong to non-positive integer for any positive real root. And the second condition is that the Q span of integral root is the same as Q span of positive real roots, where integral roots is roots whose pairing with lambda is integer. So this is called integral root system. And irreducible highest representation is called admissible if the highest weight is admissible. So it looks, definition looks a bit technical, but the meaning of this definition is the following. So the first condition means that the casualistic corresponding casualistic polynomial is trivial. So this means the character of this representation can be written as alternating sum over the corresponding integral roots. So it has wildcat type character form, where, so this is an integral root, while group generated by reflection corresponding to integral root. So this character formula is almost the same as character of integrable representation. And the second condition means that the second condition means that the this integral root system is isomorphic to an affine root system. So it's not finite. It's not finite and contains translation part. So so because it contains translation part, this character can be written as alternating sum of theta functions associated with this affine root system. So this implies that this character has a modular invariance property. As in the case of integral representation. And the conjecture of Kac-Moody, which is still open, is that the all modular invariant representation of G hat are admissible representations. So this admissible representation have a nice property that the character are modular invariant. And it also true that this category is semi-simple, as in the case of integral representation. So this is a very nice category, which is larger than the category of integral representation. So I want to consider the case when this simple affine vertex algebra is admissible representation. In fact, and you can check that so this simple affine vertex algebra is admissible if and only if a shifted level is some positive rational number such that P is not so small. So P is greater than dual Coxeter number or Coxeter number. This is Coxeter number. So this denominator is mutually prime to R check, and it's mutually prime to R check, and when it is not. Where R check is a Leysin number. So it's a number of maximal edges in the linking diagram. So R check is 1 or 2 or 3, and 1 for ADE, and 2 for BCF, and 3 for G2. So this contains the case when K is a non-negative integer. So if you choose Q to be 1, this condition just means K is non-negative integer, but there are cases when Q is not 1. So there are quite many admissible affine vertex algebra which are not integrable. And there's a conjecture of Drazen and Miller's, which was proved by Adamowicz Miller's for SL2. This is already now proved. This is proved by Adamowicz Miller's and Parse for type B and half integer level, and Axtel proved by still B for G2 at some special cases, and myself in general, that if LKG is admissible, then if you consider the category of representation in the category O, then this is semi-simple. And moreover, we can describe simple objects here. So this is a lambda with admissible of level K satisfying some conditions. So it's a subset of level K admissible representation. And because there are only finite many admissible representations, this in particular means that the number of simple objects are finite. But there is a difference. So at this, up to this point, representation theory is quite similar to that of integrable affine Kac-Moody algebra. But the difference is the following. So however, this category of weight representation is bigger. So we have positively relaxed highest weight modules which are not in the category O, and we have weight representation which are not even positively graded. And this category is not semi-simple. So it's more interesting than the category of integrable, that of integral representation. And for, yeah? I think it's not semi-simple. It's not semi-simple, yeah. Yeah, and so the classification of simple module is done by Adam H. Millers in the case of SL2, and by Slava and Enric Ramirez and myself for SL3. And in general, it was done by Kawasetsu and read out general. So we know the classification of simple objects in this category of weight module. So actually, it's thanks to the result of Slava. It's enough to classify simple relaxed modules, and this is done by Kawasetsu and readout in general. And the number of simple objects is infinite. So this is much wider category than the category of integral representation. And here comes our theorem. So unfortunately, we could do it only for SL2, but I think this is already interesting. So G is admissible. LKG admissible, not integrable. So the first statement is that this category has enough projectives. It's a bit surprising because the category of weight modulo of SL2 did not admit enough projectives. And second statement is that if you consider a principal block of this category, so this is equivalent to the category of unrolled small quantum group. So zero means principal block. The block containing this representation, and this one is for trivial representation. And UT unrolled. This is unrolled quantum small quantum group, which is a semi-direct product of usual small quantum group with enveloping algebra of Cartan. So because this small quantum group has only finitely many number of simple modules, so we need somehow enlarge it by giving extra grading. And T is E2 pi I. Maybe I write on the right. E is E2 pi I k plus h, which is a primitive root of unity, where Q is a denominator of k plus h. Yeah, sorry, T. So this statement is only for SL2, but we believe this should be true for in general. So the statement would be, so if LKG admissible and Q is prime to our check, then the same hold. So it has enough projective and principal block should be isomorphic to equivalent to the unrolled quantum group of Lagrange dual of G, where T is the same, given by the same formula. So let me make some words. So first for, so correspondence of affine Kac-Moody and quantum group has been done by Kazran Lustig. And so we have a category O, and here we have smaller category of Kazran Lustig, so which is, so G, we can consider the small g acts the category on which the small g acts semi-simple. And the Kazran Lustig showed that this category, when k plus h check is not positive rational number, then this category is equivalent to the category of finite remainder representation of UQ of G, where Q is e to pi I over k plus h. And if you compare this statement and that statement, you see some difference. First of all, so they consider a negative level. And here we consider positive level. And the Q, so k plus HF appear here in denominator, but here appears numerator. So the correspondence is quite different. And so the principal block, the only object in the principal block which belongs to category O is those, so this some product, so only this one belongs to intersection. So this equivalence is really perpendicular to the equivalence of Kazran Lustig. So I'm supposed to stop at 10 minutes before. So I make one more remark. So another remark is that if you have vertex algebra in general, you can associate a Poisson variety called associated variety. And then one can show that if LKG is admissible, if LKG is admissible, then one can show that the associated variety has of this form. So maybe I skip this part. And so this is, one can show that this is a closure of some nilpotent form. And this condition looks like so-called restricted Nulucon, if you are familiar with modular representation theory. And in fact, one can check using result of Ginzburg, Kumar, and Bendal, Nakano, partial, and Pilen. This is isomorphic to a spectrum of cohomology of small quantum group. Where T is defined by the same formula. So the same small quantum group appear here for the associated variety, but here not unrolled, but it's a usual small quantum group. And we think this is not a coincidence that the same small quantum group appear. And we think there should be a connection to 3D gauge theory. But we don't have a precise statement yet. So maybe I stop here. Project, yeah, we are allowing, yeah, you're talking about L0. Yeah. L0 node, yeah. Yeah. So this is, we want to understand this kind of, in terms of 3D mirror symmetry. So it's natural that the G Lagrange appear. One side G and one side Lagrange.
Conjecture, you put a condition for simple laced.
No, we didn't.
That
R check and Q. So this is a condition, but this does not imply. Yeah.
But you know that if this is not the case.
Then I think this has to be replaced by G, but I'm not so sure. Yeah.
And just to confirm, that on the right-hand side, this is just category O?
Yeah, this is a module which belongs. Yeah, this is module in the category O. Yeah, this is category semi-simple.
Right. And so from the beginning, by definition, your weight modules have finite dimensions.
Finite, yeah.
Do you have any idea what happens if you relax this?
Actually, we still not sure whether it's enough to consider. It's okay to restrict ourselves to the module with finite dimensional weight spaces.
So we don't know.
We don't know yet. Yeah. level 0 is not admissible. That's very wide. For isolation, they are only admissible or critical or integrable. So there's nothing special, but for example, level -2, D4, so this kind of thing should be very interesting, but much more wide.